Hello, here we are going to learn LCR series resonance. First, we will see the difference in functioning of resistor, inductor, and capacitor connected in an AC circuit. Then we'll see what is the potential difference across series combination of inductor and capacitor and how it changes with respect to frequency of the applied AC signal. We will then see the change in current in the series LCR circuit with respect to frequency of the applied AC signal. From there, we will discuss the concept of resonant frequency and then we'll plot a resonance curve. From the curve, we will then discuss the concept of bandwidth of resonant circuit and quality factor of resonant circuit. Simulation of LCR series resonance is shown in another video, the link of which is given here in the description box. Let us now see the difference in functioning of resistor, inductor and capacitor when they are connected in an AC circuit. We know that potential difference across a resistor is given as I into R, and hence current flowing through the resistor will always be in phase with potential difference developed across it. Here we can then show current as well as potential difference across a resistor along the same axis, and we are showing here along positive x-axis. In case of an inductor, potential difference developed across an inductor is equal to L into di by dt, which shows that VL is not directly proportional to current flowing through the inductor, but it is directly proportional to the rate of change of current flowing through the inductor. If current flowing through an inductor is a sinusoidal signal as shown over here, we can see that at omega t equal to 0, current in the circuit is 0, but di by dt, that is rate of change of current, will be maximum at this point, which will develop maximum value of potential difference across the inductor. At omega t equal to pi by 2, current flowing through the inductor will take maximum value, but at this point di by dt will be equal to 0 and hence VL, that is potential difference across the inductor, will become 0. From where we can clearly see that potential difference developed across an inductor will always be leading the current flowing through it by 90 degrees. When current is then shown along positive x-axis, VL will be along positive y-axis. What will happen with capacitor? In case of capacitor, we can write current flowing through the capacitor, that is I is equal to C into dVc by dt. Comparing this equation with the equation for potential difference across an inductor, we can see that now current is directly proportional to rate of change of voltage across the capacitor. And hence, in case of capacitor, potential difference across the capacitor will be lagging behind the current flowing through it by 90 degrees. So, if current is shown along positive x-axis, potential difference across the capacitor will be along negative y-axis. Hence, if we connect an inductor in series with a capacitor so that current flowing through them is the same current, we will notice that potential difference across an inductor and that across the capacitor will be 180 degree out of phase with each other. Let us now compare variation of reactance of inductor and that of capacitor with respect to the applied frequency. Reactance of an inductor is directly proportional to the frequency of current flowing through it. It is given as 2 pi f into L, whereas that of capacitor is inversely proportional to the frequency of current flowing through it, and it is given as 1 upon 2 pi fc. So if we compare XL and XC, which are changing with respect to frequency of the current flowing through them as shown over here, we can see that at a certain frequency, XL will be equal to XC. This frequency is denoted as F suffix R. For frequencies below FR, XC is greater than XL, and at frequency much less than FR, XL will become negligibly small compared to XC. Whereas if we increase the frequencies beyond FR, XL goes on increasing and XC goes on decreasing, and at a very large frequency then XC will become negligibly small compared to XL. At frequency FR, XC is equal to XL, and so if inductor and capacitor are connected in series having the same current flowing through them, IXL, that is VL, will be equal to IXC, that is VC. But we know that VL and VC are 180 degree out of phase with each other. Having same magnitude of the voltages across L and C with a phase difference of 180 degree, the potential difference across the series combination of L and C will then become 0. When we connect a resistor, an inductor and a capacitor in series with each other and connect an AC voltage source across this series combination, using Kirchhoff's law, we should be able to write Vs equal to Vr plus Vl plus Vc. But here we have written it in vector form. Why should it be like this? It is because Vr, Vl and Vc are not in phase with each other, and so we need to write the equation in a vector form. As we have seen, the change in VL and VC with respect to frequency, let us now look at this particular diagram. If we are having a frequency of the AC source which is beyond frequency FR, at which XL is greater than XC, and so VL will have a higher value compared to VC, which will give us VL plus VC along the positive y-axis. VL plus VC plus VR, where VR is along positive x-axis, should be equal to Vs, and that means VR will have the value as shown here in this diagram. If we go on increasing the frequency, VL will go on increasing as XL is going to increase, but XC is going to decrease, and so VC is going to decrease. The source voltage Vs is going to remain the same. So the resultant magnitude of VL plus VC plus VR is going to remain the same, and that vector Vs will move along the semicircle having radius Vs. As we go on increasing the applied signal frequency beyond FR, VL plus VC will go on increasing. This will decrease VR because Vs has to move along this semicircle only. That shows that as we go on increasing the frequency beyond FR, the phase difference between the applied voltage and current in the circuit will go on increasing, and it will take maximum value of 90 degrees when the frequency becomes much greater than FR, where Vc becomes negligibly smaller than VL. When Vc becomes negligibly smaller than VL, we can say that the circuit is going to be inductive circuit. What will happen if signal frequency is decreased below FR? When the frequency is decreased below FR, now XC will go on increasing and XL will go on decreasing. In this case, VL plus VC will take a value which will come along the axis of VC. That means now Vs will be along the part of the semicircle which is coming in this fourth quadrant, which shows that the Vs is now lagging behind the current in this circuit. This phase difference will take maximum value, that is 90 degrees, when Vc is much greater than VL, and that will happen for a frequency which is much lower than Fr. At this frequency, which is much less than Fr, circuit will work as a capacitive circuit. From this, it is clear that Vr is changing with the frequency of the applied signal. At F equal to Fr, VL plus Vc is equal to 0, giving us Vr equal to Vs. When we decrease frequency below FR, as VL plus VC goes on increasing, VR goes on decreasing, keeping VS constant. Similarly, when we increase the frequency beyond FR, again VL plus VC goes on increasing, which will decrease VR as VS is going to remain constant. Maximum value of VR will be then equal to Vs when VL plus Vc is equal to 0, which happens when applied signal frequency is equal to Fr. Up till now, we have noticed that at F equal to Fr, XL is equal to Xc, which gives us VL equal to Vc, and they will have 180-degree phase difference between them. From the vector equation Vs equal to Vr plus Vl plus Vc, we can see that at F equal to Fr, Vs will be equal to Vr. That means at F equal to Fr, the LCR series circuit works like a pure resistive circuit. Current in the circuit can be given using simple Ohm's law as VR upon R. Hence, we can see that at frequency of the applied signal equal to Fr, current in the circuit will have a maximum value, and that will be equal to Vs upon R. We have noticed that as the frequency of input signal changes on either side of Fr, potential difference across the resistance decreases. That means current in the circuit also decreases. We can understand the change in current in this LCR circuit looking at the change in impedance of the circuit. Impedance of the series LCR circuit is given as Z is equal to square root of R square plus XL minus XC whole square. Thus, this Z will have a minimum value when XL minus XC becomes 0. At F equal to FR, XL is equal to XC, which will make impedance to be equal to minimum value, and this minimum value will then be equal to R. Current in the circuit I should be equal to Vs upon Z. This current will then be equal to maximum when Z is minimum, and hence when F is equal to Fr, current I will take a maximum value, and this I maximum will be equal to Vs upon R. What is this frequency Fr about which we are discussing so far? The frequency Fr about which we have discussed so far is called as resonant frequency of the series LCR circuit. So, resonant frequency of an LCR series circuit can be defined as the frequency at which impedance of the circuit will be minimum, and that will be equal to pure resistance in the circuit. It is also a frequency at which current in the circuit will be equal to maximum value, and that will be equal to the applied voltage divided by resistance in the circuit. We can derive equation for the resonant frequency knowing the fact that at this frequency XL is equal to XC. Hence, we can write 2 pi Fr into L is equal to 1 upon 2 pi Fr into C, which implies Fr is equal to 1 upon 2 pi root LC. From this equation for the resonant frequency, we can see that resonant frequency of series LCR circuit depends on the value of inductance and capacitance in the circuit. It is independent of pure resistance in the circuit. So, what is the concept of resonance in series LCR circuit? Resonance curve for series LCR circuit is a graph of current in the circuit versus frequency of the applied signal. At the frequency of applied signal equal to Fr, which is decided by the inductance and capacitance value in the circuit, we find that current in the circuit is maximum, that is equal to Vs upon R. The two frequencies corresponding to the points A and B at which the current has dropped to I maximum upon root 2 are called as two cutoff frequencies of the resonance curve. The 2 points A and B are called as half power points. Power consumed by the circuit is given as product of RMS value of the applied voltage and RMS current in the circuit, and cos of phi, where phi is the phase difference between the applied voltage and current in the circuit. When the frequency of the applied signal is equal to resonant frequency Fr, we have seen earlier that applied voltage is in phase with the current in the circuit. That means phi is equal to 0, giving us cos phi as the maximum value equal to 1. And hence, at resonant frequency, power consumed by the circuit is maximum, and that will be equal to I maximum square into R. Power is consumed only by pure resistance of the circuit. At points A and B, that is at frequencies F1 and F2, which are called as cutoff frequencies, the power consumed will be equal to I maximum upon root 2 square into R, because at these 2 points the current has dropped to I maximum upon root 2. Hence, the power consumed by the circuit at the 2 points A and D will be equal to I maximum square into R upon 2, that is the maximum power consumed by the circuit at F equal to Fr divided by 2. And hence, these 2 points A and B are called as half power points. This power is consumed only by pure resistance of the circuit, and so it is called as true power. As frequency of the applied voltage goes on increasing beyond Fr, phase difference between applied voltage and current in the circuit will go on increasing. In the same way, as frequency of the applied signal decreases below Fr, again phase difference between the applied voltage and current goes on increasing. This decreases the value of cos phi, and that shows that as frequency of the applied signal changes from the resonant value of the circuit, power consumed by the circuit goes on decreasing. Over a complete AC cycle, power consumed by a pure inductor as well as by a pure capacitor is always zero. Why average power consumed by a pure inductor or a capacitor over one complete AC cycle is always zero? As we have seen earlier, in case of pure inductor as well as in case of pure capacitor, current passing through it is out of phase with the potential difference across it by 90 degree. And hence, you can notice from these two graphs that product of current and voltage for inductor as well as for capacitor is not always positive through the one complete AC cycle. For first 1/4 if it is positive, for the second 1/4 it is negative, for the third 1/4 again it becomes positive, and the fourth 1/4 it becomes negative. In the same way, for capacitor also it is changing for every 1/4 of the input cycle, and hence over one complete cycle of the input signal, the average power consumed by pure inductor as well as by pure capacitor is 0. Whereas in case of resistor, current flowing through it is always in phase with the potential difference developed across it, and hence throughout the cycle the power, that is product of current and voltage, is always positive. And hence in an LCR series circuit, power is consumed only by a pure resistance of the circuit. Let us now define bandwidth of series LCR circuit. We have already studied resonance curve of a series LCR circuit, which is a graph of current in the circuit versus frequency of the applied signal. At a resonant frequency, current in the circuit is maximum, and also the power consumed by the circuit is maximum. Whereas we have defined points A and B as half power points, where current in the circuit is I maximum upon root 2 and the power consumed becomes half of the power consumed at the resonant frequency, which has a maximum value. The input signal frequencies F1 and F2 corresponding to the half power points on the resonance curve are called as cutoff frequencies. F1, which is less than the resonant frequency, is called as lower cutoff frequency, whereas F2, which is greater than the resonant frequency, is called as upper cutoff frequency. The difference in these two frequencies, that is F2 minus F1, is called as bandwidth of the resonant circuit. And hence, bandwidth of the LCR series circuit is nothing but range of frequencies over which power consumed by the circuit is greater than or equal to half of the maximum power that is consumed when the frequency of the input signal is equal to resonant frequency. In practice, the resonance curve is always plotted for current I against log of frequencies so that we can cover larger range of frequencies. In that case, the two cutoff frequencies will be obtained in terms of log of F1 and log of F2. And hence, to calculate bandwidth, we need to take anti-log of the readings corresponding to the 2 points A and B. Let us now define quality factor of series LCR circuit. For series LCR circuit, quality factor is defined as the voltage magnification in the circuit at resonance. Hence, it is given as voltage across either inductor or capacitor in the circuit at resonance divided by supply voltage in the circuit. Hence, quality factor denoted by Q is written as Q equal to I maximum into XL upon I maximum into R, where I maximum into XL is the voltage across inductor at resonant frequency and I maximum into R is equal to the supply voltage. Similarly, I maximum into XC is the voltage across the capacitor at the resonance, and hence this Q is also equal to XL upon R at resonance, or it is equal to Xc upon R at resonance. Writing XL equal to 2 pi Fr into L and Xc as 1 upon 2 pi Fr into C, and then substituting the equation for resonant frequency Fr as 1 upon 2 pi root Lc, we will get equation for the Q factor as 1 upon R into root L by C, which shows us that quality factor of a series LCR circuit can be increased by using an inductor which has high inductance value but low internal resistance. Quality factor of the series LCR circuit is also given as resonant frequency divided by bandwidth of the circuit. That means for the LCR series circuit to have higher quality factor, bandwidth of the circuit should be kept as low as possible. Larger quality factor also shows that the circuit has good selectivity for the resonant frequency. Let us now see the effect of changing pure resistance in this series LCR circuit. Pure resistance value in the series LCR circuit decides the maximum current at the resonance, whereas resonant frequency depends only on the value of inductor and the capacitor. It is independent of resistance in the circuit. As we go on increasing pure resistance in the circuit, we will find that maximum current at resonant frequency will go on decreasing and the resonance curve will become flatter. Sharpness of the resonance curve indicates that as the frequency of the input signal changes from the resonant value, current in the circuit will drop faster. The LCR circuit is used as a tuning device in radio sets or TV sets. In these sets, we need to tune to a particular frequency, the broadcasting at which is of our interest. And we don't want the mixing of broadcasting happening at other frequencies, and hence it is desired that the frequency changes a bit, suddenly there will be drop in the current in the circuit. To have a sharp resonance curve, then it is essential to have pure resistance of a small value in the circuit. From these three curves, we can see that as the resistance in the circuit goes on increasing, not only that the curve has become flatter, but it increases bandwidth of the circuit. We just now saw that Q factor of the circuit is also written as resonant frequency upon the bandwidth. Change in the resistance of the circuit is not changing the resonant frequency, but it is increasing the bandwidth, and hence the Q factor of the circuit will go on decreasing as the resistance in the circuit increases. This shows that Q factor also decides selectivity of the LCR series circuit. The circuit with smaller pure resistance will have higher Q factor and it will have a good selectivity for the resonant frequency. What we have studied up till now. We have seen the LCR series resonance circuit, which has inductor, capacitor and resistor connected in series with each other and gives a resonance curve, that is a graph of current in the circuit versus frequency of the applied signal as shown over here, having a peak at a frequency that is called as resonant frequency, and the value of resonant frequency depends on the values of inductor and capacitor in the circuit. This resonant frequency is calculated as 1 upon 2 pi root LC. At the input signal frequency equal to the resonant frequency, the supply voltage Vs will be in phase with current I in the circuit. This current will have maximum value at the resonant frequency, and that value will be equal to Vs upon R. Bandwidth of this circuit is given as F2 minus F1, where F2 and F1 are the upper and lower cutoff frequencies, that is the frequencies corresponding to half power points of the circuit. Quality factor of the circuit is given as 1 upon R root L by C, which is also equal to resonant frequency upon bandwidth of the circuit. It decides how good the circuit is in selecting the resonance frequency. This circuit hence has applications for all the tuning devices like radio sets and TV sets.